Hello students, today we are going to discuss electrostatics. In that Gauss law of electrostatics we are going to discuss. Why I am saying electrostatic, because this Gauss law also we have in the magnetism also, that's why. So Gauss law is most important topic in the electrostatics, because using this one we can able to calculate the electric field intensity of a charged bodies in easy way and without any much complicated of using integrations and differentiation methods. So what we are going to learn in this Gauss concept, that is Gauss law of electrostatic concept, what we are going to learn. We have three concepts that we are going to learn here. One is what is the flux concept. First one is flux concept, and second one is what is Gauss law, statement of the Gauss law. Third one is applications of the Gauss law. These are the 3 points we are going to discuss today. Now we are going to discuss the first concept, that is concept of flux. Flux we are indicating with the letter phi, symbolic representation. What is this concept of flux? Flux is nothing but group of concept. What is a group of concept? Group of line concept. What is line means? Nothing but, you know that whenever you take any charge, due to charge there is electric line exist, and not only one line, many number of lines are exist due to charge. So if you take any linear charge distributed body, due to this we are getting number of electric lines are here. These electric lines, if we taken as a group, these are called group of electric lines. That group of electric lines is called as flux. That means simply number of electric lines is called as flux concept. So you can see the statement of this one. Statement is equal to group of electric lines is called as flux. So if you apply this flux to the air, that is called air flux. That means air can be divided into layers. Water can be divided into layers. If you apply it to the water, that is called water flux. If you apply it to the magnetic field, that is called magnetic flux. If you apply it to the electric field, that is called electric flux. So this is electrostatics. That's why we are calling that group of electric lines, this group of electric lines called as electric flux. We are calling that electric flux, we are indicating with the letter phi. Now we are going to discuss about the flux equation. How we are going to represent the flux equation. Now here consider one of the area. This is having some surface area, that is one of the region area. Area is a vector quantity. Area is a vector quantity. This is always in the direction of the normal, that means perpendicular to the direction of the surface. Suppose example, if you taken this is the area, okay, my hand is the area. So the line which you taken perpendicular to this is the line which you taken perpendicular to this is called normal. Area is the vector quantity. The vector quantity always along the normal direction. So this is the direction of the area vector. That is, you have to keep it in mind. That is unit vector based. I explained here. This is the direction of the area vector, I can say. Now, if the group of electric lines, already I told now, group of electric lines called as flux. This group of electric lines, when passing through that area, that is called flux is passing through that area. That okay, that flux can be explained in terms of electric field like this. These group of lines called as electric lines. These electric lines, when they are passing through the area, the flux can be explained like this. The flux, we are expression like this. It is the okay electric lines. The flux is nothing but electric lines which are passing through unit area, passing through the area. So passing through the area means, according to the concept, flux is a scalar quantity and electric field is vector quantity. Area is also vector quantity. When you take the two vectors, when you multiply, you are getting a flux. That means electric lines passing through area is called as flux. So in this case, if you calculate this one, the scalar quantity we are getting due to product of the two vector quantity means it follows the one of the dot product, we can say. That means flux is one of the scalar product, we can say. According to that one, I can write this is the flux can be defined as it is a product of magnet of the electric field, magnet of the area into cos of the angle between them. So this is the expression for flux. That is called flux equation. Flux equation is equal to mod E mod S cos theta. Now this flux we are measuring in terms of SI unit as a Webers we are measuring, and this one we are measuring in terms of CGS unit as Maxwell. Maxwell is the units of this one. Mostly we are using which one? Weber only we are using Maxwell unit. Okay, we are not all using, most of the times we are going to use Webers only. This is the one of the concept we discussed, right? Now come to the case of discussion of cases. What are the cases? If that means first, okay, I will classify in terms of Okay, cases. First, case 1. If theta is equal to 0 degrees, what is the meaning of theta is equal to 0 degrees? 0 degrees means, here if you observe here, flux we are defining, it is a product of electric field and area into cos of the angle between them. So this theta indicates the angle between electric field and area. So if you observe the case of this one, this is the direction of the electric field and this is the area. If both are in the same direction, then theta is equal to 0. I can example I will tell you. And if we come across a case of this, my hand is the area, okay, but that area vector is in this direction. So this is the direction of the area. So if the electric lines are passing, this pen I taken, these electric lines, if we imagine these electric lines are passing as you're looking like this. So what is the direction of the electric lines? The direction of the electric lines is in the direction of the area. Both are parallel. When both are parallel, what is the angle between them? 0. When angle between them is 0, in that case, the flux across that one is equal to maximum. So what base we can say? Using the formula. Phi is equal to E into S into angle is cos 0 degrees we have. So what is the cos 0 value? That is 1. That is nothing but E dot S. So flux is equal to magnitude of the electric field, magnitude of the area, that gives the maximum flux. This is called maximum condition, maximum phi. If phi, okay, theta is equal to 0 degrees, flux will be maximum when angle between the electric field and area is 0 degrees. This is the first case. Now what is the second case? Case 2. If you come across a case of, okay, case 2, here if theta is equal to 90 degrees, if we chosen, what is the meaning of 90 degrees? Electric field and area vector must be perpendicular to each other. For that, to understand that one, so what I am taking is, I am taking the diagram of that area. So if you observe this one, this is the way the surface area chosen. In this case, this is the normal, already we discussed, and this is the surface, along the surface. Now this is the normal vector, that is called surface area vector. Now electric field is passing as you are looking like this. Now in this case, the electric field is passing as you are looking like this. This is the way the electric field is passing. If electric lines are passing like this as you are looking like this, in this case, what I can write, electric lines are passing in this fashion. So that means they are making how much angle? 90 degrees with the normal. So if the electric field is making an angle 90 degrees with the normal, in this case, I can use cos 90, because according to formula, phi is equal to Es into cos 0, okay, cos theta. Here theta is equal to how much we have to take? Theta is equal to 90 degrees if we choose. So what concept you will get? Cos 90 value is equal to, you will get 0. 0 into anything? 0. That means in the case of case 2, okay, in the case 2, what I can write? If theta is equal to 90 degrees, in that case, the flux is equal to nothing but E into S into cos 90 degrees is equal to totally becomes 0. So that means what is the flux? 0. So here most important concept is, if electric field is passing, this is the surface area, if the electric field is passing like this, perpendicular, flux will be maximum. If electric field is passing like this, flux will be minimum. Simply, if you want to understand, is a pipe. If you say pipe, my area is a pipe. If you say water is coming, the water will comes maximum through area. Along the area, the water will not flow along the area. Practically also, if you see that water will not flow like this, water comes out from this. So along the surface, flux is minimum, and normal to the surface, flux is maximum, basing on a case 1, case 2. So here I can say electric field and surface area both are in the same direction, mean theta is equal to 0 degrees I can write. And along this direction, if the electric field is in this direction, in this case electric field and both are surrounded an angle of 90 degrees I can say. While applying the flux equation, while solving the problem, you have to take care a little bit what is the nature. We can write the expression also another way we can understand here. So I taken this the one of the surface area. The surface area normal vector is like this. Now this surface area, before we taken, okay, the surface area line is along vertical, but in this case what is happens, it is tilted some angle here. How much angle? That is theta. So that means this is the normal line. Before, this arrow mark direction is the normal line, but now this is the normal direction. So the area vector is along this direction. Now we are applying the electric lines. The electric lines are horizontal. In this case, this is the direction of the electric lines. I can see group of electric lines. So I taken only one line here. When electric lines are passing, as they are looking like this, from the through the area. In this case, what is the flux enclosed in this? You can calculate the flux enclosed in this area in two forms. According to concept, this is a product of electric field and area vector, electric field vector and area vector. Now in this case, if you observe here, this area surface is tilted a little bit angle theta. So that's why what happened, the normal not in the direction of electric field. Now in this case, this normal is making an angle theta with respect to electric field. When it is making angle theta with the electric field, now what we have to do, either you can take the surface area in the direction of the electric field, or area you can take in the direction of the surface area, because we are calculating the maximum flux concept based on that. So first, if I want to calculate the surface area, you take it in the direction of the electric field. So surface area is a vector quantity. So if you resolve into components, you will get S cos theta is in the direction of the electric field in terms of magnitude, only magnitude. So the flux is a scalar quantity. In that case, I can write as that is the product of electric field into what is the area component along the direction, that is you can take it as S cos theta. If you take in the area component, what you are going to get the formula, flux equal to Es into cos theta. Similarly, I can also take the E in the direction of the S. If you take in the electric field in the direction of the S, what you are going to get in this direction, I will get E cos theta. I can resolve. You will get E cos theta. If you take in the flux formula in that direction, maximum flux equal to, in that case also I can write as E cos theta into surface area. That means area vector. So in this case, if you rearrange the terms, again you will get the same thing as what you got in the previous, that is Es cos theta. So there is no much variation. There is no variation in the both the equations here. That means you need to understand while solving the problem, either you can take the electric field component in the direction of the area, or you take the area vector in the direction of the electric field component, electric field. So that what happens, you can get the flux magnitude according to the asking question, because sometimes they will ask along the x-axis, sometimes they will ask at a particular direction of the angle. So based on that one, you have to use the component method. That component method, along the which direction they are asking, that direction you have to take the components and you have to calculate the required flux in that direction. Now we are going to discuss about most important concept, that is Gauss law. Who is Gauss? Gauss is a scientist. Gauss is explained about calculation of electric field intensity due to charged bodies at any point of distance r from the charged body in easy way without any application of much integration methods. So what is the concept he taken? What way he explained? First, he taken the concept of group of lines concept called as flux concept. Using the flux concept, he explained about the Gauss law and he able to calculate the electric field due to that charged bodies. One. Next, in this case, he chosen the bodies having some surface areas. Surface areas are areas. So the bodies which are having surface areas and areas, then you can apply the Gauss law directly there. Suppose if you're not having bodies, not having surface areas, still you can use the Gauss law by considering by imagining one of the surface areas of the body. That is only we need to understand how to apply this one. We'll just discuss in the next. So Gauss law is calculate the electric field intensity due to a charged bodies using the flux concept by taking the surface area of the bodies concept. The use of this one is the complicated problems can be done in easy way using the Gauss law, using the flux concept. And the flux concept nothing but what? Group of electric lines concept. That's why you can see the statements here. What are the things we are going to cover in the Gauss law? Gauss law is complicated. Calculation can be complicated calculations in the electric field can be done easily using Gauss law. One. Next, using flux concept, he calculated the electric field due to charged bodies. And third one, to apply this law, we have to know the areas of the surfaces and areas of the surfaces and areas of the bodies we need to know. So that means if we don't know the area, you have to imagine that area. How to imagine that areas, that we can. So we have some discussion. After that, we'll continue that applications in the next topic. To explain further statement of the Gauss theorem, consider one of the body which contains the charges Q. Now, how much flux is present in that body? What he explained is the flux enclosed in that body is equal to, he is stating that 1 by epsilon naught times the charge enclosed in that body. This is the statement given by Gauss. Gauss stating that the flux enclosed in a closed surface area, is equal to how much? 1 by epsilon naught times the charge enclosed in that area. That means 1 by epsilon naught is the magnitude into charge. More the charge, more the flux, less the charge, less the flux, is stating that. In this case, if you taken the positive charge, then the flux is also positive. In the case of negative charge, the flux is also negative. So there are two types of flux we have according to the type of charge. If the charge is positive, positive flux. If the charge is negative, negative flux. And we have some concept of explanation of that flux lines also. Here we can discuss in that. So what way we can discuss? Electric lines started from one point and set other, right? So in this case, if you observe here, these are the electric lines which are entering into the body. This is the way the electric lines are entering. So these are called group of electric lines or electric lines. Now these are electric lines which are entering. After that, what happens? These electric lines are going away from the body. This is the way the electric lines will passes away from the body. So I taken some example lines. The electric flux, which are entering into the body and leaving from the body. This is called entering flux we are calling. This is called leaving flux we are calling. Entering flux and leaving flux. So if there is any charge, there is a flux is there. If electric lines are entering, then in that case, entering flux we have to take it as positive, and the leaving flux which is there, that we have to take it as negative. So from the any body, if a flux is going away, that you have to take as negative. If any flux lines are entering into the surface area, that you have to take as positive. So based on this one, we can conclude some derivation. First we'll complete the statement of the Gauss law, and we'll go for equation of that. Before going to the statement, you take one more. I taken one of these surface, one of the body having surface area. In this we have a charges, that is Q1, Q2, minus Q3 and minus Q4. These are the charges we have. Now what is the flux enclosed in that closed surface area? According to Gauss theorem, what is the flux statement? Charge 1 by epsilon naught times the charge enclosed in that surface area. So in this case, to explain the flux, to calculate the flux enclosed in this, more than one charge is present, he is stating that you have to take the net charge enclosed in that one, that is net charge by epsilon naught. That means 1 by epsilon naught times the net charge. What is the meaning of 1 by epsilon naught times the net charge? That is nothing but phi is equal to 1 by epsilon naught times the total charge. What is the total charge? One is positive charge Q1, second charge is Q2. Charge is a scalar quantity, so it is always set to Q1 plus Q2, but here we have a minus, so minus Q3 minus Q4. So this is called as net charge enclosed in that closed surface area. So the flux enclosed in the closed surface area is equal to 1 by epsilon naught times the net charge enclosed in that area. So that is a concept is called as Gauss law. Now come to this case of statement. What is statement? According to Gauss law of electrostatics, the flux enclosed in a closed surface area is equal to 1 by epsilon naught times the charge enclosed in that surface area, is called as Gauss law. That is only we have discussed just what we done. This is called as net charge, that is equal to 1 by epsilon naught times, this is 1 by epsilon naught times the charge enclosed. Which charge? Net charge or total charge enclosed in that closed surface area is called as Gauss law of electrostatics. This is important. And now expression for the Gauss law. According to the competitive examination, this is a statement you need to understand. According to competitive examination, what I can write here, the flux is equal to nothing but simply net charge by epsilon naught. This is the equation for this one. So here our discussion of this one, the flux is, there are two types of flux we already told, positive flux, negative flux, and also we can write this term flux in terms of electric field concept also, because we know flux is nothing but that is electric field into surface area. Now, if you apply this formula here, what you are going to get, E into S is equal to, that is nothing but Q by epsilon naught. I can write the formula of this. This is the expression is called as Gauss formula. E into S equal to nothing but Q by epsilon naught. We can apply. So, suppose if you want to apply this one for the different bodies, now how to apply that different bodies we can able to discuss now. How we are applying the Gauss law expression for this in the case of one of the example surface area body taken here, one of the football here. So football is hollow one and it is having surface area. So suppose if you imagine that it is a sphere, we given the charges onto this one. These charges will be accumulated on the surface at different points, you know that, right? So the charges will be accumulated on the surface of this. Now, so what we are going to do is, what is the flux enclosed in this, or what is the electric field due to this one at a point, if you want to calculate. Suppose if you want to calculate the electric field at this point due to this one. Now from the center of the that football, what distance that point is present. First you have to take that line. This is the line I am taking here. This is the line along which the point is taken from the center. After this, according to the distance of that one, the electric field will be depends. You know that this is the center of the football, right? Now in this case, to calculate the flux due to this one, first this is the having surface area, you take as capital S, total surface area, but this surface area is not a small one, big one. So we have many number of charges are there. So here we have to integrate actually using mathematical tool, but using Gauss theorem we can able to calculate easily. How? He taken the group of line concept. What he taken? Group of line. That means if you observe this one, and here I am taking the lines here. Okay, if you observe this one from here, this is the patch I taken here. This is one charge which is there. This is a charge which is, now this charge is in this patch. You can see the patch here. Football contains the patch. So this patch having conical surface. It is 3-dimension. If you taken the lines of that one, it forms like this, right? So if you observe this one, that means if you taken a charge, due to this charge, what happens? Number of electric lines will be passes through this one. Number of electric lines will be passes through this one as a looking like this. This way the electric lines are going to passes, using that small area of that one. So why I am taking this one? Because of if you choose and then that small portion, then you can able to calculate for complete portion. This, whatever the small portion I choose in, this portion is called as ds. Now according to the Gauss theorem, I can say the electric field due to through this area is equal to, you take it as E. The surface area which is in small elementary surface area, that is ds, because due to one charge. Now at what point you are calculating? At a point, but due to this small area, how much flux is coming out to calculate according to Gauss theorem? How much? That is Q by epsilon naught I can take. So now what you can apply? You can apply the integration here. If you apply the integration, then you can get the required solutions here. So what way of required solution we can get it? So in this case, electric field is constant because it is uniform charge density. So E into integral ds is equal to, that is nothing but Q by epsilon naught you have to take. Integral ds equal to, you will get S, that is E into S equal to Q by epsilon naught you will get. So what is S here? Surface area of the body. That surface area of the body you can apply according to the type of body which is contains the surface area. So Gauss formula expression can be explained by considering the unit surface area at a point, and by calculating the flux across that unit surface area. By using integration in a simple form, you can apply for complete surface area of the body. So that formula is called as Gauss formula. Now this Gauss formula we are applying for different applications. Now we are going to discuss that applications of this Gauss law. Now we are going to discuss applications of the Gauss law. In the applications of the Gauss law, we have different way of calculation. That different objects we are going to take for the calculation of electric field intensity due to that charged bodies using Gauss law. First one is charged sphere. In the charged sphere, we are calculating electric field inside, on the surface, outside. Second one is in the case of charged cylindrical drum, and in the case of charged wire, and a charged sheet. That is, there are two types of sheets we have concepts: thin sheet, thick sheet. And last, we are going to discuss about flux across the different bodies, like applications for the objectives like a hemisphere. Okay, and in the case of cubical bodies, in that cases we are going to discuss the flux across the different types of charged bodies. We can able to discuss according to the position of the charge, like that. So first one, we are going to discuss about which one? Applications in that charged sphere. Now come to the case of first application, that is charged sphere. In the case of charged sphere, now we are calculating inside the sphere. Inside means this is the one of the sphere okay, taken. Now this sphere having center and having radius. The radius of the sphere you take it as r. Now we charge this one. When the charges are given, these charges will be accumulated on the surface of the sphere. You know that this is a basic concept of any charged body. When the charges are accumulated on the surface, now what is the electric field intensity inside? Using Gauss law, how we can able to calculate? So if you want to apply the Gauss theorem, first you have to understand that if there is a charge in the closed surface area, then there is a flux will be there. If there is a flux, there is electric field intensity will be there. No flux, no electric field intensity. So directly I am calculating the here concept of flux. What is the flux is there present or not? Based on that, the electric field is there or not. We can check it. Now here the charges are on the surface. Now you take an inside. So if you want to calculate inside, first what you do is imagine anywhere inside. So imagine there is a actually the charge inside. Now you have to imagine a Gaussian surface here. What surface? Gaussian surface. When you choosing the Gaussian surface, that Gaussian surface construction is must be, you can take it like this. This Gaussian surface you can take it inside like this. Anywhere you can take it up to, okay, within this region. That means if you want to calculate electric field here, so what is electric field intensity here means you have to take the Gaussian surface here. If you take on the Gaussian surface, at what point you want to calculate? Suppose I want to calculate the electric field intensity at this point A. So construct the Gaussian surface. It is similar to the body. That is called imaginary Gaussian surface. What is called? Imaginary Gaussian surface. That imaginary Gaussian surface, if you chosen, now check it that inside that Gaussian surface we have any charges are there or not inside. So inside the closed surface we are not having any charge. Q is equal to 0 because we have only charges on the surface. So when there is no charge, what is the flux? Flux equal to 0. Simply when the flux is 0, electric field also 0. So simply we can say that electric field intensity inside any sphere, which sphere? Hollow sphere, anywhere is 0 because there is no charge enclosed in the closed area. So according to the Gaussian surface, inside the Gaussian surface we are not having charge inside. That's why flux is 0, electric field also 0 here. Now we are finding electric field intensity due to the same charged sphere on the surface. On the surface means this is the one of the charged body. Now you take the point here. This is the point. At this point, that point is I am calling as B point. Now what is electric field intensity at this point you want to calculate? For that I taken A, one of the charges on the surface, so charges will be accumulated. Now what you have to do is you have to imagine a Gaussian surface at that point. If you draw the Gaussian surface at the point B, what shape you have to draw the surface exactly equal to the shape of the body. So here this body already having sphere, so construct the sphere. So if you construct the Gaussian surface, the Gaussian surface also comes exactly on the surface of the body only, so that is both are same only. This is the Gaussian surface. Now if you observe the charges, actually the charges will be little bit inside on the surface, but little bit inside, not completely inside. So that means what is the electric field at this point? The electric field at this point is due to this charges will be present. So what is the distance from here to here is the radius r. So now in this case I can apply, there is a flux enclosed in this one. The flux enclosed is equal to what is the charge of this body? That is total charge is equal to Q. If you say that is Q by epsilon naught is the formula. Now to calculate the electric field intensity at B point, which is a distance r from the center to surface. Now what is according to concept of Gauss? Flux is equal to E into surface area of this one. Okay, the surface area of that one, if you want to calculate, that is equal to ds you can take, and is equal to Q by epsilon naught. So here to calculate here, what we have to do is just you have to imagine a small surface area here. This small surface area called as ds. Due to this, there is the electric field intensity exists across the normal, that is E. Now calculate the electric field intensity due to this small elementary portion. Then after apply the integration for complete surface area. So integral ds equal to q by epsilon naught is the formula. In this case, you have to integrate for the surface area for complete surface. So in this case, to apply here, first what is the formula according to that one? E into integral ds is equal to what I can apply, that is s is equal to, that is q by epsilon naught I can write. So that is E into what is the surface area of the sphere, complete sphere, that is equal to 4 pi capital R square is the surface area of that one, because R is the radius of that, and that is only the radius of the Gaussian surface also. So that is equal to, I can write as q by epsilon naught. So from this, what is the electric field intensity? I can write as this 1 by 4 pi epsilon naught, that 4 pi R square, make it that side, it becomes q by, this is 4 pi R square into epsilon naught you will get. If you write in an order, I can write as 1 by 4 pi epsilon naught into q by r square. So this expression already we discussed in the case of definition also. Electric field intensity due to sphere is equal to 1 by 4 pi epsilon naught q by square of the radius of that sphere. So that means this is the electric field intensity on the surface. Using Gauss theorem, just using 2 steps, we can able to calculate the electric field intensity on the surface. Now next one, we are calculating the electric field intensity due to this charge sphere outside distance of r. You can calculate. So here from the center, I taken the sphere here, this is a line, this is outside point. Now at this point, I want to calculate the electric field intensity here at this point P. So what is the distance of this one? The distance of this one from the center is equal to small r. What is capital R? Capital R is the radius of the sphere, that is capital R. So the point is a distance of a small r. So to find the electric field intensity due to this charged body, this is the charged body which is contains the number of charges, that is total charge of this body is equal to how much, that is capital Q. Now what we have to do to calculate the electric field intensity at any point using Gauss law, first you have to imagine a Gaussian closed surface having surface area. So at this point P, I can construct one of the closed surface area. So what shape that surface area must be? That is exactly the same like the body. So in this case, whatever the surface area I am choosing here, this is the way I am choosing the surface area. So this is the way I can choose the surface area here. If you observe that the surface area which I taken, that is imaginary surface area which I taken, this imaginary surface area contains, the point P. It is touching, passing through the point P. Now what is the radius of that imaginary Gaussian surface? Small r. Original sphere is capital R, imaginary Gaussian surface is small r. At this point we are asking to calculate. So for that, first what I am doing is I am choosing a small surface area on this sphere. The total surface area of this imaginary Gaussian surface is taken as capital S, and I chosen a small surface area here, that is called as ds. Same like what we discussed in the previous football. You take a patch of football, calculate the electric field due to that patch. So this is the patch I can take. Now what is the electric field due to this small portion, that is equal to ds. Now electric field always exists normal to the surface for any case of the charged body. In this case also, the small surface area, through this small surface area, electric field will be parallelly outwards like this. This is the direction of electric field in this case. Now we need to find that electric field intensity at that point. To find the electric field intensity through that small area, just apply the formula for this. What is the formula? Flux is equal to, okay, according to Gauss theorem, what is the flux? That is total charge enclosed, okay, in that area. How many times? 1 by epsilon naught times. So here already charge is there. If you see that all the charges Q, all the charges are within the Gaussian surface, that means I can say that is Q by epsilon naught is the formula for this one. What is flux here? E into S. In the case of S, we are just calculating for small surface area, that is E into ds equal to, that is Q by epsilon naught I can take. Now this we can apply integration here. If you apply integration, that is E into integral ds equal to S I can write, that is nothing but Q by epsilon naught I can write. So that is nothing but E into what is S, surface area of the Gaussian surface which you taken, that surface area. Actual surface area is capital R, radius. Imaginary surface area having radius is small r. So what is the surface area of the imaginary surface? That is 4 pi into small r square you have to take, not capital R square. That is important here. That is q by epsilon naught. So that means what is the electric field intensity? I can write as, if you write in order, directly 1 by 4 pi epsilon naught. That is capital Q by small r square. This is the electric field intensity due to this charges sphere at a point P outside of the charges sphere. That means always you have to choose the surface area. Which surface area? The Gaussian surface area where you taken that surface area to take. If it is inside, that means if the charge is present, there is electric field. If no charge, no electric field. Suppose if that surface area is on the surface, the body surface area only becomes the Gaussian surface area. If the point is outside, then in that case, you have to construct the surface area similar to the actual body surface area, but that surface is bigger one. That bigger surface area you take it as 4 pi smaller square. This is a concept we have to apply in the case of charged spheres. Now we are going to discuss the electric field due to charged cylindrical drum using Gauss theorem. So first consider one of the drum. The length of the drum is L, cylindrical drum having length L and radius capital R, which is charged one. Given charges, as you can see, the charge on this one is capital Q. Now we are going to find the electric field intensity at 3 points. A point you can see inside, B point on the surface, C point outside. Now the point which is on the outside, which is at a distance of smaller. The point which is inside is a distance of, okay, anywhere inside you can take it as, you can take as RA if you want to take. This is the axis of the cylinder. If you say, this is the axis of the cylinder, if you say, with respect to this axis of the cylinder. So in this case, the point A is at a distance of, I can write as RA. The point B is at a distance of RB, I can write. So first, to calculate the flux at what point? A point. So first case, at flux at A point, to calculate flux at A point is equal to, first you have to construct a imaginary surface at that point. Anyway, inside, if you see the inside, if you construct any surface, always you have to construct the Gaussian surface similar to the given surface. So I can construct a Gaussian surface as you are looking like this. A small cylinder you have to construct, where if you observe this one, the point is on this small cylindrical surface, whatever may be the length which you chosen. Later we'll discuss, because here we no need to spend much time, because of in this, according to Gauss theorem, the flux will be takes place when there is a charge enclosed in that is equal to 1 by epsilon charge enclosed in that surface area. But in this small cylindrical surface area, we are not finding any charge, because the charges are on the main surface area of the cylinder. Inside there is no charges. So Q is equal to 0 here. Q is equal to inside, that is QA is equal to 0. There is no charges at A point. So automatically the flux enclosed in the region is equal to 0. So there is no electric field intensity present inside. This is the first concept. Second, if you come across the case of second point, where is the second point? On the surface. On the surface, if you want to calculate, then we can go for the derivation of this one. On the surface means that is equal to, what is the distance of the point? The distance of the point is at RB. Now here, to calculate the electric field intensity at B point, just imagine a small surface area. Imagine a small surface area here on the surface. Okay, and before that we have to draw the imaginary Gaussian surface also. At this point, the point is on the B, means you have to construct the Gaussian surface. The body surface only becomes as a Gaussian surface at that point. In this case, the small surface area which you chosen on that one is equal to ds, I can say. Now, due to this elementary portion ds, there is electric field exists. Okay, at that point, that means outside, I can say this is electric field intensity E, I can say. So according to the concept of flux at B point is equal to, I can write as, that is Q by epsilon naught, I can write. That is according to here, I can take it as QB is equal to, that is pi B flux. So at B point, the flux at B point is equal to Q by epsilon naught, I can write. Now what is flux at B point? Flux at B point is equal to electric field into, okay, that is surface area of that small B point here is equal to Q by epsilon naught. So now you have to apply the integration here. So where you have to apply the integration? Here you have to apply the surface area. So here if you observe this one, the body which is contains the surface area, the charges are only on the curvature. If you say this is the cylindrical surface, if you say this is the curvature, on this curvature only the charges are present. If you say according to that one, the surface area of the cylindrical surface you have to take according to that one E into, okay, that is E into integral ds equal to S, I can write, that is Q by epsilon naught, I can write. Now that is equal to E into, what is that surface area? I can write that small, okay, the surface area in terms of 2 pi r into, that means r is the radius of that one, okay, that radius is equal to how much we can write, that radius is equal to capital R, I can write here, capital 2 pi r into length of that cylinder. This is the surface area of that cylinder. Circumference, this is the circumference of the cylinder, that is 2 pi r, that is 2 pi capital R into length of that. Up to what length it is? That is length of, total length of the cylinder is capital L up to this length. So this, if you take in the cylinder, what is the total surface area of this third part? Means you take a small cut off piece that acts like a circle. The circle length is 2 pi r and the length of that one total is L. So E into 2 pi r into L is equal to, I can write as Q by epsilon naught, I can write. So from this E is equal to what I can write, that is if you make it that side, it becomes into, that is 1 by 2 pi epsilon naught into, okay, Q by R into L. Now what is Q by L? Q by L is called as charge per unit length, is called as lambda. So E is equal to, okay, that is nothing but 1 by 2 pi epsilon naught, that we can write as lambda. So simply lambda by 2 pi epsilon naught R. R is also is there. This is the formula for this. Which one? Electric field intensity due to this cylindrical surface on the surface. Now we need to discuss about outset point. Outset point is important. So that is the required derivation for us. Now if the point is outside, that is C point. So already we discussed, this is one of the charged cylinder which is having length L. So L is the length of the cylinder. R is the capital R is the radius of the cylinder. Now point is outside, which is the distance of R. Now to explain this concept, so first we need to understand the at what point you need to calculate. So for that, you have to take a little bit distance so that we can easily understand this. So in this case, the point I am taking a little bit near to reduce the area of this, okay, problem. So I chosen the point here, that is C point. So to explain the concept of Gauss theorem, so you have to apply the, okay, you have to construct the Gaussian surface here similar to the same body. So here also I am taking the Gaussian surface that is on that point. So construct the Gaussian surface at C point. For that I am taking the diagram of this one as they are looking like this. So I taken one of the Gaussian surface and which is passing through that point C as you're looking like this. Now this is one of the biggest, okay, cylindrical surface we got here. The radius of this cylindrical surface, now it becomes smaller. The length of the cylinder you take it as, that is smaller. Now what you have to do, we have to apply the concept of this. To explain the concept of this one, first choose the elementary portion here. If you choose the elementary portion, the electric field at this point will be always outwards. So at this point, if you choose the point, so imagine the surface. So electric field at this point, due to that charge sphere inside is, this is the direction of this one. Because the imaginary Gaussian surface inside, we have a complete charge surface. Due to this charge, every point on the imaginary Gaussian surface, we have electric field intensity. So for that, I choose an elementary portion of length ds. So according to Gaussian, okay, Gauss law, what you can say, the electric flux is equal to, okay, is equal to q by epsilon naught, right? We can write. So what is phi? Phi is equal to nothing but electric field into small elementary surface area ds is equal to q by epsilon naught. I can write. Now integrate this one. So integral ds equal to, anyway I can write as s only, that is s equal to, that is q by epsilon naught I can write. So but here we have to take care of one small thing here. So while you are doing this one, how many surface areas the body contains, that is also we have to take it into consideration here. So in this case, the surface areas of the body is equal to E into integral. We have totally 4 surface areas, 3 surface areas we can take it here. This is one surface area. I can take, this is the another surface area, top one, and below one another surface area. This is I am taking as S2, and this is another one S3, and this outside surface area I am taking as S1, S2, S3. Totally 3 surface areas we have. So the whatever the S we got, this is the sum of the 3 surface area, that is S1 plus S2 plus S3. 3 surface areas is equal to q by epsilon naught here. Now if you apply this one, E into S1 plus E into S2 plus E into S3 is equal to q by epsilon naught, we can write. Now what is electric field across S1? Electric field across S1 already we can calculate, because there is a electric field is coming out of this one. What is the electric field at S2? Where is S2? This is S2. What is the direction of the electric field according to the concept of this? This is the direction of the electric field at this point also. What is the direction of the electric field at S3? This is the direction of the electric field. So if you observe the S2 and S3, this is the normal vector, that is area vector of S2. This is the area vector of the S3, and both are perpendicular to the surface area, that is 90 degrees, make an angle 90 degrees. This is also making an angle 90 degrees. In both the cases, what happens? The flux enclosed in this closed area is equal to how much you are getting? 0. Here also the flux across this one becomes 0, because electric field always exists normal to the surface. The flux also always passes normal to the surface. So in this case, it is passing along the surface. The flux is 0 due to this electric field. So here the contribution of electric field, flux across the S2, electric field across S3, that is anyway 0. So I can write as simply E into S1 is equal to q by epsilon naught. What is S1? S1 is the surface area of the first one. So what is the surface area of the first one? I can write as, okay, E into, what is S1? Surface area of this. What is the surface of the imaginary Gaussian surface? That is nothing but the length of the cylinder is 2 pi L into, okay, because the cross section, if you take in this point, this is the way I can take the circumference of that one, and across the length gives the total area, that is 2 pi L into, okay, that is total is 2 pi L into, sorry, R is the radius, no, not 2 pi L, that is 2 pi R into, because R is the radius of this one. What is the radius of this one? This radius you have to take. This is the circumference of that one. The circumference is 2 pi R into length of the cylinder is how much? Yeah. Is equal to how much I can write? Q by epsilon naught I can write. So from this, what is electric field intensity is equal to, I can write as 1 by 2 pi epsilon naught R into Q by L I can write. What is Q by L? Nothing but lambda. Lambda, that is nothing but E is equal to lambda by 2 pi epsilon naught R I can write. It is a similar way of expression which you got at on the surface also. On the surface you got lambda by 2 pi epsilon naught capital R you got, and outside at any point you got lambda by 2 pi epsilon naught small r you got. That means in this case I can say the electric field intensity due to this charged cylinder is inversely to just distance of that point. Lambda is constant, 2 pi epsilon naught is also constant. So this is a way you can able to explain the electric field intensity due to this charged cylinder using Gaussian surface simple form. Actually we extended by taking number and directly using the 2 steps. Look at this one, this is 1 step, 2 steps, and this is 3. Using the 3 steps you will get the derivation of this. Now next application we are going to discuss about charged wire. Consider one of the linearly charged wire which is having negligible thickness, having only length. So of length L, I given a charges onto this, that is as you are looking here, the total charge of this wire is equal to capital Q. Now at a point of distance, suppose I am taking the point here, at this point of distance, I am calculating the electric field intensity due to this charged wire using Gauss theorem. Actually, electric field intensity due to this linearly charged wire, we calculate using integration method. That taken long time. So in this case, we can complete it in a short way. So first, what is the point of discussion here? At what point you want to calculate? At that point, you have to construct the Gaussian surface first. That is important concept for our discussion of this. So Gaussian surface while you are constructing. So first, what is the shape of the body? Here, this is the wire. Wire not having any surface area, but you have to, if you want to calculate the electric field intensity due to that charged wire, so you have to imagine a Gaussian surface which contains a surface area. For that, what I am doing is, imagine that this wire is, if you see microscopically, if you see the wire microscopically, it look like a cylinder. So that means I can construct this wire, for this Gaussian surface, I can construct as a cylinder. So for that, what I am doing is, I am taking the cylindrical surface here as I am looking here. This size I can modify, and while you are taking this cylindrical surface, what is the concept here? The line point of that, it must be touches the point here. This is the point I chosen here. At this point I want to calculate. So at this point, the cylinder, imaginary cylinder I taken here, that is called Gaussian cylindrical surface vector. That Gaussian cylindrical surface now constructed. Now you calculate the electric field intensity due to this Gaussian electrical cylinder, Gaussian electrical cylindrical surface you calculate. So for this, if you see this one, this line charges are inside the Gaussian surface. So the point which you chosen, what is the distance of the point? The distance of the point is, you take it as r, small r. Now that small r only becomes the radius of this Gaussian surface. What distance the point you chosen, that is only becomes the radius of that Gaussian cylindrical surface. What is the length of the cylinder? L. The wire, what is the length of the wire we chosen? That is only the length of the cylinder it becomes. Now, how many surfaces this cylinder contains? The cylinder contains 3 surfaces. This is one, S1, and this is bottom point, bottom surface, this is S2. Third one is curvature. For that curvature, I am taking a surface, that is S3. Now to calculate electric field, what is the direction of the electric field across each surface area? This is a linearly charged body. That's why the electric field at every point, the electric field at every point, if you see that, the direction of the electric field, in the case of S1, this is the positively charged body. That's why the electric field always in this direction, it will be outward in the direction of the point. Because we chosen the point outward in this direction, that's why this is the direction of the electric field across this surface area S1. But S1 is a surface area. What is the direction of the area vector? This is the direction of the area vector, that is N1. So both are perpendicular to each other. Perpendicular means what is the flux enclosed in that? That is equal to 0. So in this case, I can say here electric lines are passing across this one, means otherwise the fluxes lines are passing across this one, means electric field is equal to 0, we can say, across S1. Similarly, in the case of S2, how the electric lines are passes? In the case of S2 also, electric lines will be passes like this, and in this case also both are perpendicular to each other, that is 90 degrees. So in this case, because normal vector I can take it as N2 like this, N2 cap, normal vector, and these two are 90 degrees separation. So electric field in this case also 0. But what is the electric field due to this small portion curvature? Imagine a small, imagine a small surface area. The small surface area I am writing as ds3. Now due to this positive charge, there is electric field across this one. That electric field across passing through this one is not 0, that is equal to E, because the area of ds3 is in the direction of this is N3. So electric field and area vector both are in the same direction, so flux will be maximum. So I can write here net flux is equal to, in this case is equal to, I can write flux across the first surface plus flux across the second surface plus flux across the third surface. Anyway, the flux net flux is equal to, what is the flux across first surface? 0, because electric field is 0. Second one also, below also 0. Only we have a flux across third surface, that is phi 3. So net flux is equal to, that is nothing but phi 3 is equal to, according to formula we can write q by epsilon naught times the charge enclosed. That means 1 by epsilon naught times the charge enclosed in that. So what is q here? If we replace here, the q is equal to, we can replace. Okay, what is q3 here? We can write the q3 value. Q3 is, okay, sorry, phi 3, flux phi 3. What is flux? According to concept, electric field into area. What is the area of that pi? Okay, flux, that is small area ds3. Flux equal to into area. What is the area? That is ds3. That means electric field across that small elementary area ds3 is equal to q by epsilon naught, we can write. So now you have to integrate this one. So if you integrate this one, this becomes E into S3, integral ds3 equal to S3, that is q by epsilon naught you will get. So what is S3? Surface area of that cylinder. What is surface area of the Gaussian cylinder here? That is nothing but, it is having radius small r, so the circumference of the cylinder is 2 pi r into length of the cylinder is L. This is the surface area of the cylinder, 2 pi r into L is equal to q by epsilon. Now if you apply the condition for this, what you are going to get? In this case, the electric field E is equal to, I can write as, that is 1 by 2 pi epsilon naught r into, I can write as q by capital Li. What is q by L? Nothing but, according to charge per unit length, is called as linear charge density, that is 2 pi epsilon naught r into, I can write as lambda. So here also if you observe this one, E is inversely to R. So in the case of cylindrical surface, R, in the case of wire, linear charge, okay, charged wire, the electric field intensity at any point is inversely to R, and the remaining factors are all are constant. So it is similar to the previous derivation, but only thing is how we are choosing the surface areas. We are choosing the 3 surface areas, and according to that we have to calculate the electric field intensity. So the expression for electric field intensity at any point due to linearly charged wire is equal to, what is the formula? E is equal to lambda by 2 pi epsilon naught r is the formula for it. This is important to note.